Hello friends and welcome to edupediaworld.com, your destination to online education. Friends, from many sessions we are discussing the characteristics of element and the variation of characteristics in the groups and periods of the modern periodic table. As we already discussed in the discussion, the valence electron, valency, size of atoms, metallic character, chemical reactivity, nature of oxides, we also understood many and main physical properties with the variation of all these characteristics of element in the modern periodic table as we move down the line in a group or when we move left to right in a period. So today friends we shall discuss and learn about the ionization energy and the variation of ionization energy in periods and groups in the modern periodic table. So friends, let's start with the ionization energy. Well, we will first understand the meaning of ionization energy and then we'll describe the variation among the elements in a periods and group of the modern periodic table. So friends, what is ionization energy? Well, we know that an electron in an atom are attracted by the positively charged nucleus. Like you can see here, well friends, you can see here it is a nucleus with positively charged protons and neutrons with the null charge, and there is a orbit where the electrons keep on revolving around the nucleus. So when we have to extract one electron from the attractive force of the positively charged nucleus, then there is some energy has to be supplied to overcome the strongest attraction of this nucleus. And when the electron gets removed like this, you can see here it has been removed from an atom, then an atom acquires 1 unit of positive charge and becomes a positive ion. So you can also see like this. We know that, let's understand like this. We know that we have equal number of protons and equal number of electrons in a stable atom. Or you can say stable element. Now, if we minus 1 electron, obviously there is a number of protons is now greater than the number of electrons. So we get a positive ion when we extracted or remove 1 electron from a stable atom of a gaseous element, or you can say that we remove 1 electron from the stable atom. So where we get the ion, that is positively charged ion, plus 1 electron which has been removed by some energy, we call it ionization energy. So now friends, we can now say that the ionization energy of an element is the minimum energy required to remove an electron from a free gaseous atom of that element to form a positive ion. Friends, please note that the unit of the ionization energy is kilojoules per mole. So more than 1 electron can also be removed from an atom one by supplying more and more energy. In fact, if we talk about the ionization energy levels, we have basically 3 levels. That the energy required to remove the first electron from the neutral gaseous atom to form a single charged positive ion, we call it a first ionization energy. Let's understand by some descriptions. We have first ionization energy, or you can also write ionization energy, that is when we remove first electron from a stable atom, right? Now, the energy required to remove the second electron from a singly charged positive ion to form a doubly charged positive ion, we call it a second ionization energy. Like, second ionization energy will be when we remove the second electron not from the stable atom, yes, from the single positive ion. And third ionization energy when we remove the third electron from double positive ion. Well, friends, by this we can say that as we increase the positive charge on the ion formed, the subsequent or the continuing ionization energy on the increasing tone, there is a higher than the previous one. That is, the second ionization energy is more than the first ionization energy, and the third ionization is still higher than the second, and so on. So in our discussion, we will consider only the first ionization energy of the element, which will be written as ionization energy only, and the unit will be kilojoules per mole. Friends, I'll take an example of these ionization energy levels by giving, like, we know that when we remove an electron, there's an energy which has been added to remove the electron from a stable atom. We get a positive ion plus we remove an electron. So this is the basic equation of first ionization energy. We can say that only ionization energy. I'll take an example of magnesium to show that the higher levels of ionization energy is always greater than the lower ionization energy. That is, the second ionization energy is greater than the first ionization energy, and third is similarly is greater than the second ionization energy and first ionization energy. So here we take the magnesium, we get an ion plus electron. This is the first ionization energy, which have 738 kilojoules per mole of energy is required to remove the first electron. Then we remove the second electron, we get the doubly charged ion. It is the second ionization energy, which have 1451 kilojoules per mole of energy. Then again we remove the electron from the doubly charged ion. We get the third ionization energy, which is almost 7731 kilojoules per mole. So by this you can see that the energy levels goes on increasing when we keep on removing the electrons. Now friends, let's sum up the discussion of the ionization energy. That is, each succeeding energy level is higher than the preceding energy. That is, just I have described you. Second is, further away an electron is from the nucleus, easier it is to be expelled. Obviously, the attraction between the positively charged nucleus and the electron is much lesser than when it is farther from the nucleus. Ionization energy is a function of atomic radius. Yes, obviously, because when the atomic radius is large, the attraction of the electron to the nucleus is more than the attraction of the atomic radius, which is having a less radii. It is easier to take electron from a larger element than the lighter element. So now let's discuss about the variation of ionization energy in the periodic table. First, we shall take the variation of ionization energy with respect to periods. When the ionization energy of an element increasing on moving from left to right. Friends, this trend is not regular. There are some bumping stations. For example, I have taken the third period element with sodium, magnesium, aluminum, silicon, phosphorus, sulfur and chlorine with their respective ionization energy. Please note that this is the first ionization energy we are keeping in mind and in the discussion with the unit kilojoules per mole. You can see the trend where there's 495 kilojoules per mole of sodium, then we have 738 kilojoules per mole of magnesium, then there is a slight slip in the aluminum with the 578 kilojoules per mole. When again it start increasing with the silicon with 786 kilojoules per mole, it start increasing in with the phosphorus too. Then there is a small slip in sulfur. So let's understand this variation when it is moving into the increasing order, but there is a small variation between the periodic table in the periods. You can see this graph with the variation of the first ionization energy of period 3. Let's understand one by one how the variation and why the variation is occurring. Friends, we know that the ionization energy is dependent on atomic radius. So friends, we know that the ionization energy is dependent on atomic radii. Let's explain by the example of period 3, where we can discuss that the atomic radii goes on decreasing when we go across the period from left to right, as When we go across the period, the number of valence electron increases. The valence electron increases. So the number of proton also increases in the nuclei. So this, the same energy level as well as the increasing proton in the nuclei, this causes a strong attraction of each valence electron by the nucleus, which results in smaller atomic radii. So we conclude that when there are, as the number of electron increases, the number of proton increases, which increases the attraction of electron with positively charged nucleus, which decreases the atomic radii. Now let's explain the second point, which is the ionization energy increases because, as we have just explained, that when we go across the period, the number of valence electron increasing the same energy level as well as the increase in the proton in the nucleus. So this causes a strong attraction of each valence electron by the nucleus, which results in smaller radii. Because of this, it takes large amount of energy to remove the valence electron, and therefore the larger ionization energy is required. So now we conclude that the number of electrons increases when we move from left to right across the period. The number of protons also increases, which results in increasing attraction of electron to the nucleus, which also results in decrease of atomic radii, and which gives rise to the increase of the energy to remove the valence electron against the attraction force of nucleus. So as we discussed, there is a variation, but we also know that there are some slips in the across the period. Let's discuss the slips, why it happens. Now friends, let's see the graph where we know that the sodium is with the ionization energy. Let's see the sodium to magnesium, which is increasing with the ionization energy. As from Na to Mg, the ionization energy increasing because even though magnesium has one more electron than sodium, the electrons are going into the same energy level, which means that they are the same distance from the nucleus. Therefore, the size of atomic radii does not affect the ionization energy to increase. So this is the reason why magnesium has a high ionization energy, and because of this, the stronger attraction by the nucleus on the valence electron due to one more proton difference in magnesium. And then the strong attraction means that they will be harder to remove magnesium valence electron, therefore needs more and more ionization energy with respect to sodium. Now friends, let's understand why there is a slip from magnesium to aluminum. That is, there is some decrease in magnesium to aluminum. Why it happens? As the ionization energy decreases because the aluminum valence electron has entered into new sub-energy level, which will be discussed in the higher classes. And this is further away from the nucleus that the magnesium valence electron in the third orbit, and the increase in distance plus the combination with the shielding effect of the inner electron of the aluminum, which causes a weak attraction between the nucleus and the valence electron. Therefore, it will take a less ionization energy to remove the aluminum valence electron, and in this case, the increase in atomic radii has a major impact rather than the attraction of the nucleus. So now let's understand why there is a slip from Al to silicon to the phosphorus. That is, there is a continuation increase in the ionization energy, as these ionization energy, because even though the number of electron increases, the number of electrons are going into the same energy level respectively, meaning that they are the same distance from the nucleus. Therefore, the size of the atom radii does not affect the ionization energy to increase. And this is the reason why the ionization energy increases is because of the increase in number of protons in the nucleus. And when you go across a period, this causes a stronger attraction by the nucleus on the valence electron due to the increase in proton. So the stronger attraction means that there is harder to remove the valence electron and therefore needs more ionization energy. Now let's understand the status from the phosphorus to sulfur. As from the phosphorus to sulfur, the ionization energy slightly decreases because the third p electron in phosphorus are all unpaired. As in the sulfur, two of the third p electrons are paired. Therefore, there is some repulsion between the paired electron in the same subshell, and this reduces the force of their attraction to the nucleus. So the lesser energy is needed to remove one of these paired electrons, that is needed to remove an unpaired electron from the phosphorus. Friends, if I conclude this whole reason, we can say that from in the ninth grade sections, we can say that it is just due to the shielding effect, because the subshells and the shell, the filling of subshells of the electron and the subshell, you'll study in the details in the higher standards. Now friends, let's understand why we have a continuation increase from sulfur to chlorine from to argon as the ionization energy because increases, because even though the number of electron increases, the electrons are going into the same energy level again, meaning this, they are the same distance from the nucleus, therefore the size of a atom radii does not affect the ionization energy to increase. As the reason why the ionization energy increase is because of the increase in the number of proton in the nucleus, and when you go across a period, this causes a strong attraction by the nucleus on the valence electron, and due to this, we have an increase in ionization energy. As strong an attraction means that it will be harder to remove the valence electron and therefore need the more ionization energy, even though there is a still repulsion from the electron pair up in third p orbits and the attraction of the nucleus charge is greater than the repulsion. So there is a continuation increase in the ionization energy between the elements. So friends, now let's understand why we have a variation in ionization energy in the groups. As in groups, we know that the ionization energy of the element decreases on going down in a group of the periodic table. As friends, let's take an example of the elements of group 1. We have lithium, sodium, potassium, rubidium and cesium with the symbol Li, Na, K, Rb and Cs. With the respective ionization energy, you can see of lithium is 520 kilojoules per mole, sodium with the 495 kilojoules per mole, potassium with the 418 kilojoules per mole, rubidium with the 403 kilojoules per mole, and cesium 374 kilojoules per mole respectively. Now if we look at this periodic table carefully, we'll find that the ionization energy of group 1 element decreases gradually on going down in the group, as the ionization energy decreased from 520 kilojoules per mole in lithium to 374 kilojoules per mole in cesium. The decrease in ionization energy on the going down in the group in the periodic table we can explain like this: as the size of atom increases and the outermost electrons becomes more and more away from the nucleus, and this due to this the attraction between the nucleus and the outermost electron, that is we can also call them the valence electrons, decreases. Hence the less energy is required to remove an electron from the atom. So we have a decrease in ionization energy of the element when we go from top to bottom in a group. So if we conclude the trends of first ionization energy, of you can also say the only ionization energy in a periodic table with respect to groups and periods, there's a generally increase in the ionization energy when we move from left to right in a period, and there's a generally decrease in the ionization energy when we move from top to bottom in a group. Well, it is not regular, but yes, the trend says it increases in the period and it decreases in the group. So friends, I end up with my session with the ionization energy. I hope you have understood the session. Let's go to the main menu. So we covered with the concept of ionization energy in this session, with the variation of ionization in their groups and periods in the modern periodic table. So in next session, we shall learn about the electron affinity and the variation of electron affinity in the groups and periods in the modern periodic table. Thank you for watching Edupedia World videos.